Hello students, the final topic for chapter 6 is bilinear maps. What is a bilinear map? Bilinear is two linearities put together. Bi means two, right? Bi means two. And it's defined like this. Linearity with respect to the first variable. So we have the linear combination a1u1 plus a2u2. And it is separated like a1 and then the map of u1, a2 and then map of u2. Of course, this is for the first vector u, so you should be able to do the same thing for the second vector v as well, and that comes here. We have linear combination a1v1 plus a2v2, and then we have a1 times the map of v1 part, a2 times the map of v2 part. So linearity with respect to the first vector, keeping the other vector as same, and vice versa, the linearity with respect to the second vector while keeping the first vector the same. That kind of map is called bilinear map. Now, have you done this before? Yes, we have, as a matter of fact. A good example of bilinear map was the scalar product. You see, you have bilinearity right here. The linear combination for the first vector, and then we have a1 part, a2 part. We have the separation. And then the linear combination for the second vector. Again, we have the same thing. Linearity with respect to the first vector, linearity with respect to the second vector. So the scalar product is an example of a bilinear map. Now the scalar product requires symmetry as well, but bilinearity does not really require symmetry. So this vector space u and v can be drastically different. Drastically different, I mean by they don't even have to be in the same dimension. Still, we have some nice expression, and this theorem tells us that. If we have a bilinear map, it has a unique matrix associated to the bilinear map, and the matrix computation that corresponds to the bilinear map is like this. X transpose A times Y, where X and Y are coordinate column vectors. So this is a row vector, and then this is m by n matrix, and this is a column vector. For example, you may have some map like this. Let's see. Okay, 3, -2, -4. Okay, all right, that's as good as any. And then okay, 2, -3, 0, 1. Okay, all right. This kind of bilinear map, 3, -2, -4, and then this. But then again, this matrix multiplication, this 3-dimensional row vector times 4-dimensional column vector, that's not well defined. We need something in between. So this is what we need, and then I need some numbers. Okay, I just made up. This kind of thing is an example of a bilinear map. So if you multiply this 3 by 4 matrix times 4 column vector, that's well defined. And then if you multiply the first row, first column, we get one number. Second row, this column, we get another number. And then third row times this column, we get another number. So this multiplication is going to be a three-dimensional column vector. So three-dimensional row vector times 3 column vector. Okay, that's well defined. And in the end, what do you get? You're going to get a certain real number. And of course, this computation is rather tedious, and I just made up this number, so it's quite unlikely that I'm going to get something nice. But in any case, this is an example of a bilinear map. Can you see this is bilinear? Well, let's see. This is matrix multiplication up to here. So instead of the column vector right here, if you add 2 column vectors, can you separate? Yes, you can, because this matrix multiplication is distributive. So yes, you can do that. And how about scalar multiplication? That's really duh. You can always pull out scalar multiplication all the way out. No problem there. And how about doing something here? That's okay too, because if you multiply this first, then this is a matrix, and then we have something over here. And again, matrix multiplication is distributive. So if you have some row vector plus another row vector there, distribute around, yes, we can get everything done. It's bilinear, you can prove it by brute force method. But in any case, this is an example of a bilinear map. The key thing is, any bilinear map can be written in this fashion. X transpose m by n matrix times y, like this. And this matrix A is uniquely determined given the basis, kind of like matrix associated to the linear map. Okay, shall we go ahead and prove that? Okay, let's go ahead and prove that. Proof. I wrote a sketch of proof here, but this is almost a complete proof. Okay, let u1 through um and v1 through vn be basis of u and v respectively. So u is m-dimensional and v is n-dimensional. And we expect m by n matrix here. Okay, this linear combination, for given arbitrary vector u in capital U, U can be written as a linear combination of u1 through um, where x1, x2, all the way over to xm is the coordinate vectors. But then again, instead of using all those dots, I'm using the sigma notation. Try to get used to it. And then v can be written as a linear combination of v1 through vn uniquely. And coordinate vectors are y1, y2, y3, all the way up to yn in column. And then instead of this linear combination with dot, we can express it as a sigma notation. Try to get used to this, because sigma notation, if you get used to it, it's actually less confusing and it's easier. Okay, then g of u comma v can be written as g of this linear combination, comma, that linear combination. And then what can you do here? I skipped a step here, so maybe I'll just insert that step here. Okay, I just reproduce the same thing here. And there, I'm going to use the property of this G, the bilinearity, and I'm going to separate out this linear combination. I can do it like that, because we have linearity with respect to the first vector. So we can always separate out all the linear combination. Now we can do the same thing to the second vector, because we have to have linearity in the second vector as well. So we just take this sigma out again. Then that's what we get over here. And then xi times yi times g of ui comma vj. That's what we get. We're going to set this g of ui comma vj as aij. Then this thing here is going to be aij. So this whole thing can be rewritten like this, where aij is equal to that. And I change the order of multiplication. That's okay, because multiplication is commutative. So instead of xi yj times g, I have xi aij times yj. And what is this? We have this double sigma, xi ai indexes matches, and aj yj indices match. It's a matrix multiplication. So if I take an extra step here to explain this thing a little bit better, not necessarily better, I may end up confusing you even further as a matter of fact, but I'm taking the risk. Oops. Copied and pasted in the wrong place. Okay. Okay, what did I just do? And here I just multiply this common coefficient out of the summation of j running from 1 through n. And then look at this part. This is a matrix multiplication. aij, that's matrix, and then j is going from 1 through n, and only that. So that's going to be y1, y2, y3, all those rows matching the column. So it's a matrix multiplication. We have matrix A times column vector y here. And then because this is matrix multiplication, this became a m-dimensional matrix, m by 1 matrix as a matter of fact. And then combine that with this summation, then that becomes another matrix multiplication, this time row vector times a column vector. Anyway, it becomes matrix multiplication, and we rewrite using dot dot dot. It goes like this. Now, if you had a little bit of difficulty following all those sigmas, start from here and then backtrace and rewrite everything with dot 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 and see if you get the same thing you started off with. It's far more tedious this way, but if you're not comfortable with sigmas, then it'll work out. In any case, the conclusion is like this. X transpose, which is a row vector, times m by n matrix, and y. That way, we ended up with a real number. 1 by 1 matrix, so it's the same as real number. Okay, so bilinear map, going over to the real number, can be written as x transpose a y. And also the uniqueness is left to the students. Actually, that's really trivial because we just defined aij's using g of ui vj. So whenever ui and vj's are all set, we cannot have anything different. But if you really want to write everything down perfectly, then go ahead and do that. Anyway, for any bilinear maps, we have x transpose a y form. Now for scalar product, which is a example of bilinear maps plus symmetric and positive definite. Let's go back to the definition of this scalar product here. You see, bilinearity, yes, is here, but also symmetric and positive definite. And we have this for bilinear maps, for any bilinear maps. So we're going to have similar expressions for scalar product as well. But in this case, this map B is a little bit more special. It's not an m by n matrix because this time x and y are of same dimension because v and w are coming from the same space v this time. And then also v comma w is same as w comma v. We have symmetry. And that leads to a symmetric matrix. And that's not difficult to prove. And then the other thing, positive definite leading to this expression, and that's going to be really hard. I mean, we are not ready to discuss it yet because we didn't learn the determinant yet, but even after learning the determinant, this is going to be difficult to deal with. But yeah, this is not something we are going to be doing in this course. This thing is going to be really useful in analysis, multivariable analysis, and we don't typically cover multivariable analysis in this course, this curriculum. We have real analysis 1 and 2, and they are both about one dimension and some matrix spaces, but intrinsically multivariable real analysis, we don't do that, so I don't think this will ever show up. So let's talk about only this easy part, symmetry part. Okay, that's easy because previous theorem told us that such matrix B exists, and it is given by G of v comma w. So in this case, the scalar product of vi comma vj. So put those together and you're going to get matrix B. But then again, we can use the property of the scalar product. Scalar product vi comma vj is same as scalar product wj comma vi. Same because of the symmetry. These two are the same. And what did you get? Bij is equal to bji. That means B is equal to B transpose. We have to have a symmetric matrix. Now let's go back to our Module 10 notebook. Yeah, I'm done with this. Module 10 notebook, and please allow me to remind yourself an example of the example of a scalar product here. This matrix here is a symmetric matrix, and this expression fits what we just discussed. X transpose matrix B Y, and depending upon the property of this matrix, this can become a scalar product. And indeed, yes, it's an n by n matrix, 4 by 4 in this case, and the symmetric, clearly we have symmetric, and positive definite. Let me just verbally mention it. This determinant of this 4 by 4 matrix is positive. This determinant of 3 by 3 matrix is positive. This determinant of 2 by 2 matrix is positive. And finally, this determinant, this number is positive. All positive, that means positive definite. So yes, this is indeed a scalar product. The brute force computation of positive definiteness, well, you can go about all these. Here's a bit of a hint, and then you can actually prove it using complete square. Good luck.